Welcome to a groundbreaking exploration of quantum mechanics, where we dive into the revolutionized Schrödinger equation and the evolution of matter-charge. In recent years, physicists have begun to recognize a new phenomenon: charge behavior in all matter. This concept expands our understanding beyond the traditional wave nature of particles, offering answers to questions that have puzzled scientists for decades. Today, we'll journey through the evolution of these ideas, starting with the basics and moving toward the latest theoretical advancements. Let's set the stage for a fascinating journey into the quantum world, where waves and charges intertwine in ways never seen before. Wave nature of matter has been a cornerstone of quantum mechanics since its inception. Physicists have long understood that particles, such as electrons, exhibit wave-like properties, allowing them to occupy multiple positions and energies simultaneously. This duality is central to the famous Schrödinger equation, which describes how these waves evolve over time. But why do particles behave like waves? This question has inspired countless theories and experiments, leading to deeper insights into the quantum realm. As we unravel the mysteries of wave behavior, we begin to see how it connects to the newly proposed concept of matter-charge. The heart of quantum mechanics lies the Schrödinger equation. This fundamental formula allows physicists to calculate the behavior of particles in a field of force, predicting how physical quantities change over time. It's especially useful for understanding the energy and position of electrons within atoms, taking into account their wave nature. The equation has proven invaluable for non-relativistic particles, providing a framework for countless discoveries. However, as we'll soon see, its limitations become apparent when dealing with relativistic particles and the evolution of matter-charge. While the Schrödinger equation excels with non-relativistic particles, it falls short for those moving at speeds close to light. Enter the Dirac equation, which extends quantum theory to relativistic particles. Together, these equations form the backbone of matter-wave evolution. Yet even combined, they cannot fully describe the behavior of rest matter or the general evolution of matter-charge. This gap in understanding has motivated new research, aiming to create a more comprehensive framework that includes all particle states. To address these limitations, researchers have proposed a general form of matter-wave evolution. This new approach integrates both non-relativistic and relativistic particles, providing a unified description. By reformulating the Schrödinger equation and incorporating additional variables, such as charge and velocity, the evolution of matter waves can now be written for every individual aspect. This breakthrough not only advances quantum mechanics but also paves the way for understanding the evolution of matter-charge. The concept of matter-charge behavior is a revolutionary addition to quantum theory. It suggests that all matter, regardless of its state, can exhibit charged behavior alongside its wave nature. This duality means that as long as a particle has charge, it also possesses a wave, and vice versa. The integration of charge evolution into the general matter-wave equation marks a significant leap forward, allowing scientists to observe and predict charge-related phenomena in new ways. Let's revisit the one-dimensional Schrödinger equation, which forms the basis for many quantum calculations. This equation describes how the wave function of a particle evolves in space and time, factoring in potential energy and kinetic energy. By substituting new relationships involving charge and velocity, the equation can be expanded to include charge behavior, offering a more complete picture of particle dynamics. Key insight from recent research is the relationship between charge and velocity. The equation E2 equals rho hkv$ links the charge of a moving particle to its speed, Coulomb's constant, and the reduced Planck constant. This relationship allows for new substitutions in the Schrödinger equation, connecting the evolution of matter waves to charge behavior. By understanding how these variables interact, physicists can better predict the properties of particles in motion. By substituting the charge-velocity relationship into the Schrödinger equation, new forms emerge that describe matter evolution for both moving and rest particles. These substitutions reveal deeper connections between wave behavior and charge, allowing for a more general description of quantum phenomena. The resulting equations incorporate kinetic energy, rest energy, and observable wavelengths, bridging gaps in previous theories. Kinetic energy plays a crucial role in the evolution of matter waves. By expressing kinetic energy as E kinetic equals rho(12 mv2) and substituting it into the expanded Schrödinger equation, researchers can describe the behavior of particles in motion. This approach unifies the treatment of non-relativistic and relativistic particles, offering a comprehensive framework for quantum evolution. For particles moving at relativistic speeds, the evolution equations must account for the effects of high velocity. By substituting values for the speed of light and rest energy, the equations can describe the behavior of these particles more accurately. This advancement ensures that quantum mechanics remains applicable across all energy scales, from slow-moving electrons to fast-moving protons. One of the most challenging aspects of quantum theory is describing the evolution of rest matter. Previous equations struggled to account for particles at rest, but new formulations now include rest wavelength and rest charge. By substituting these values, the equations reveal that even particles at rest exhibit wave behavior with time-dependent oscillations. This insight deepens our understanding of quantum states and the nature of matter. Rest wavelength of a particle is a fundamental concept in quantum mechanics. It represents the wavelength associated with a particle at rest, determined by its mass, charge, and velocity. For particles with rest charge, the rest wavelength is given by specific formulas, allowing physicists to predict their behavior even when stationary. This concept bridges the gap between classical and quantum descriptions of matter. Evolution of matter charge is closely linked to wave behavior. As long as a particle has charge, it also exhibits a wave, and this relationship is reflected in the expanded quantum equations. For moving particles, the charge evolution equation describes how observable wavelengths and charges interact. For rest particles, the equations show that rest energy oscillates, revealing new dynamics in quantum system. Key takeaway from the new theory is that for every observable wavelength of a particle, its charge should also be observable. This principle applies to both moving and rest particles, ensuring that quantum equations remain consistent across all states. By validating these relationships, physicists can better understand the fundamental properties of matter and predict new phenomena. Particles at rest, the evolution of charge takes on a unique form. The rest charge and rest wavelength are substituted into the quantum equations, revealing that rest energy oscillates over time. This behavior highlights the dynamic nature of quantum systems even when particles appear stationary. The equations provide a framework for studying rest charge evolution and its implications for quantum theory. Velocity of a particle at rest, known as rest velocity, is determined by specific formulas involving charge, mass, and wavelength. These formulas provide insights into the behavior of rest particles, including those with no rest charge. By understanding rest velocity, physicists can further refine quantum equations and predict the properties of stationary matter. Interestingly, the rest velocity for many particles is potentially equal to the speed of light. This finding suggests a universal behavior among quantum particles, linking their rest states to fundamental constants. By exploring these relationships, researchers can uncover new principles governing the quantum world. Wave equations describing matter-charge evolution are not perfectly Gaussian, meaning they differ from classical Schrödinger or quantum Dirac equations. This distinction allows for more accurate descriptions of arbitrary velocities and complex quantum behaviors. By using factorization methods, researchers can derive general equations that apply to a wide range of particle states. For any arbitrary velocity, the general quantum equation incorporates kinetic, rest, and damping terms. These components reflect the symmetry in mass and the dynamic nature of quantum systems. By adjusting the variables, physicists can model the behavior of particles across a spectrum of velocities, from classical to relativistic to superluminal. Beta parameter is a crucial variable in the general quantum equation. It represents different aspects of particle behavior: kinetic, rest, and damping. By manipulating beta, researchers can explore transitions between classical, relativistic, and superluminal states. This flexibility makes the equation a powerful tool for quantum analysis. In quantum theory, the speed of time, denoted as J, acts as a universal speed limit. This concept helps define the boundaries of quantum behavior, ensuring that equations remain consistent across all states. By incorporating the speed of time, physicists can better understand the limits of quantum evolution and the nature of matter charge. General quantum equation includes three distinct verses: kinetic, rest, and damping. Each verse corresponds to a different aspect of particle behavior, allowing for a comprehensive description of quantum evolution. By analyzing these verses, researchers can uncover new dynamics and symmetries in quantum systems. Factorization method is a powerful technique for deriving general quantum equations. By breaking down complex equations into simpler components, physicists can model a wide range of particle behaviors. This method has enabled the development of new theories, including the evolution of matter charge and the integration of rest states. Charge-wave duality is a central theme in the revolutionized quantum theory. It asserts that charge and wave behavior are inseparable, meaning every particle with charge also exhibits wave properties. This duality is reflected in the expanded quantum equations, offering new perspectives on the nature of matter. Integration of matter-charge evolution into quantum mechanics has far-reaching implications. It enhances our ability to predict particle behavior, understand fundamental properties, and explore new quantum phenomena. By expanding the theoretical framework, researchers can tackle previously unsolved problems and advance the field of quantum science. Revolutionized Schrödinger equation and matter-charge evolution have practical applications in modern physics. From particle accelerators to quantum computing, these theories inform the design and operation of advanced technologies. By understanding the interplay between charge and wave behavior, engineers and scientists can develop more efficient and powerful systems. As quantum theory continues to evolve, future research will focus on refining the general equations and exploring new phenomena. Scientists aim to validate the expanded framework through experiments and simulations, uncovering deeper connections between charge, wave, and matter. The journey is ongoing, with each discovery bringing us closer to a complete understanding of the quantum world. Special thanks are extended to those who have supported this research, including family and mentors. Their encouragement and financial support have made these advancements possible. The journey of scientific discovery is often collaborative, and gratitude is owed to all who contribute to the pursuit of knowledge. Summary: the revolutionized Schrödinger equation and the concept of matter-charge evolution represent a major leap forward in quantum mechanics. By integrating charge behavior into the wave nature of matter, scientists have created a more comprehensive framework for understanding the quantum world. These advancements pave the way for new discoveries, applications, and deeper insights into the fundamental nature of reality. The journey continues as researchers explore the mysteries of matter, charge, and wave.